All right, well, we will go ahead and begin. As I think mentioned before, I actually looked at the textbook. I mean, I look at the textbook all the time, but um, it turns out that in the introduction, the authors say that they think the textbook could be done in a really quickly paced 1 year course. And so we're not actually intended to get through as much as I had thought. If you go back and look at the original excessively optimistic syllabus, we were going to cover all of it. Yeah.
It's a semester thing.
Yeah, but we're clearly not going to do that. So I think probably we're not even going to get to chapter 11. Probably we finish much of what's in chapter 10, and that's the end of the semester. And in some ways that's okay. This is sort of a graduate level class, and at some point grad school is about teaching yourself what you need, getting the foundation so you can then go on and teach yourself what you need to know. So yeah.
I was curious what your thought process was on the timeline for the final. Are you gonna like make it available a little bit early, or do you think you're
Right. So the final exam, it'll be a take-home final in the style of the previous two exams, and it'll be due at the end of finals week. You'll have as long as you want to do it, basically.
When will it open? Like on 14?
It will open when finals week starts, which I think is the 15th.
Sounds good.
Scheduled, if we're not going to get to chapter 11, clearly the chapter 11 study guide doesn't exist anymore, so that's going to just disappear as an option. I still owe you a problem set 3, which I've dragged my feet on because I wasn't sure how much we were going to get to. I can still make that assignment available just to help you review, though I probably will just give everybody credit for it since I haven't made it available for a long enough amount of time.
I have
So,
a question.
yeah.
Why not make 2 classes for advanced, like physical chemistry? Like it's clearly not one course thing.
Why don't you have 2 semesters of this?
Like, it's logical.
You could, you certainly could, though. The class is a requirement for first year organic grad students, and it's also an elective for senior undergraduate students, so it has that dual purpose. For the undergrad side, there's probably not sufficient interest to justify having a 2-semester physical
They will
organic
take
chemistry
it
course.
You put it and say required.
Well, sure. Actually, making things required is an interesting issue. From an undergraduate perspective, the university is not interested in majors adding courses to their requirement. Basically, if we go tell the university, hey, we thought of this great course which we're now requiring all our majors to take, they're like, oh, that's nice. Now you have to drop another requirement because they are not interested in increasing the amount of time to graduation.
There's a lot of general useless education.
We already have a lot of
Hey,
requirements
my
in the chemistry
American
major.
class is vital to my.
That's okay. And general ed, like there's a major initiative at the university to revise general ed as well. Like they're not interested in making it. Already there are some majors on campus that really honestly probably take you 5 years to complete, and they're not interested in that happening more. From a grad school perspective, there's this issue of classes versus research. What actually earns you the PhD is research, not necessarily classes. And grad school, like I say, is all about getting to the point where you have enough of a background that you can then, by reading the literature and other specialized books, teach yourself what you need to know how to do something. So, from that perspective, at a certain point, it stops mattering that you don't have somebody standing in front of you teaching you something, because you can just do that on your own. And I think that's that, plus the fact that PIs start to get a little bit antsy the more their students are in classes, because if you're in class doing stuff, you may not be in lab doing stuff. And so, yeah, there is no interest at all in a 2-semester physical organic chemistry series. There is a 553, but it's not related to this class, it's synthesis.
Yeah.
And then there are some other grad level classes in the organic area related to organometallic chemistry and natural product chemistry. We've all historically just decided that those are important topics, and you can grad students can mix and match what they're going to take. But yeah, so what can I say? You're sort of cheated by the fact that there's time. I don't know. There's just more to know than you have time to learn. So yeah.
I think they should let us have like an emphasis. Because like for an undergraduate, if I take 552 and 553 and 455,
Yeah.
all of those, I think I should have an organic emphasis on my major diploma.
Yeah, I mean, that could be. The question is, would that be worth anything to getting into grad schools?
No, but still.
Yeah. Yeah.
I want the sticker.
The longer the
You want
words on my diploma are, the better it looks.
Okay. More words, yeah. Okay. Yeah, I mean, chemistry is pretty credit heavy, though it's not even close to mechanical engineering.
Really?
Yeah. My son's a mechanical engineer, and it's going to take 5 years. And presumably they argue to the university, we cannot even lose one of these courses and still call these students mechanical engineers.
That seems kind of dubious to me.
Well,
Wow.
I'm not, yeah. It's hard stuff, so I can't do it. But all right, so Swern oxidation is something you will hear. I first learned about it when I was in grad school. Hadn't heard about it before. So these are reaction conditions you can and there are a lot of different oxidation conditions, but you can do these under some. You can do the Swern oxidation for substrates that are sensitive to strong acids, as an example. So your reagents are DMSO, which is great because that's just a solvent. People typically draw DMSO as this, but forget that sulfur is hypervalent, and the sulfur's sp3 hybridized, not sp2 hybridized. The resonance structure on the left is going to be the one that's useful to us for this oxidation because it shows you that the oxygen's nucleophilic, and then your other reagent is oxalyl chloride, or COCl2. I guess that works. All right, so the first thing that happens is sort of nucleophilic acyl substitution. That's a topic that I think we are actually going to get to in the last part of chapter 10. We have the oxygen. I'm not going to draw the arrows. The oxygen adds to the carbon to get a tetrahedral intermediate, which collapses and kicks off the chloro leaving group, giving you the following intermediate. Shoot. And the sulfur's electron poor, and by attacking oxalyl chloride, you've turned that oxygen into something that is a good leaving group. The alcohol, so Swern oxidation is usually used to oxidize alcohols. So at this stage, your alcohol starting material attacks the sulfur, and the leaving group leaves. I won't say too much about the leaving group having left, other than it doesn't stay that way. It decomposes to CO2, carbon monoxide, and Cl minus. Okay, so usually you need a base to mediate this process. Usually the base is pyridine. All right, but what you're seeing here is not that different to what you saw before for the Jones oxidation. The reagents are different, but you have a pair of electrons that used to be on oxygen. Now they're in this oxygen-sulfur bond. And if they were, so you basically have a leaving group. If we're looking for the pattern of elimination, you're looking for a leaving group on an alpha position and then a proton on the beta position. I'll show you what's thought to actually happen in solution. It would be convenient at this point simply to have a base remove this proton, do E2 style chemistry, and dimethyl sulfide leaves. However, what's thought to happen first is that these protons adjacent to the sulfur can be removed by the base, probably pyridine, to give you what's called a sulfur ylide. An ylide is a molecule in which you have a positive charge and a negative charge on adjacent carbons. So this is your ylide. Okay, and then we're going to propose an intramolecular deprotonation. You've got 1, 2, 3, 4, 5 atoms involved in that process. That's, I mean, this isn't exactly a Baldwin's rules situation. We're not doing cyclization, but intramolecular deprotonations are reasonable for 5 and 6 membered rings. So we're going to have remove this proton, electrons kick down, and then leaving group leaves. And again, those electrons from that oxygen-sulfur bond were originally on the oxygen, so that's this oxidation step. Your product is a ketone, and then the leaving group is dimethyl sulfide, which is smelly. Yep. And that comes from the DMSO. All right. I don't know that there's much more to say about that. Oh, hold on. There was maybe this. I wrote something down about a kinetic isotope effect, or rather, the existence of this ylide is supported by isotopic labeling experiments. The deuterium ends up on the dimethyl sulfide. So that's why, that's the evidence that it's not just the pyridine base that's removing the beta proton, but rather it's an intramolecular process. Okay. So that's the Swern oxidation. Anybody actually done that reaction?
We do it for 5.
Do you? Okay. On what kind of molecule?
Oh, I can't remember. This is actually the week I was gone.
Okay. All right, never actually done that, so. Okay, so now we'll talk about eliminations that form olefins. These are the classic E2, E1 type eliminations, along with some other related eliminations that follow similar principles, including sort of retroaldol, retroclason, retromichael type reactions. And we'll also talk in detail about E1CB, which is a mechanism that's maybe not discussed a ton in an introductory OChem class. So this is section 10.13, eliminations to form olefins. terrible penmanship. All right, so your standard E2 mechanism is you have a base and then you have a leaving group. I'm choosing this example deliberately. It's a tertiary carbon, so substitution is not an issue. You definitely need a good leaving group for an E2 reaction. You definitely need a good base. It's tricky to find a good base that's not a good nucleophile, and so in many cases substitution can be competitive with E2 reactions, but the classic mechanism of remove the beta proton, electrons kick down, and leaving group leaves. We'll talk about stereochemical implications and regioselectivity and all of that stuff a little bit later. We're just dealing with the mechanistic details there. So that should look familiar. 2 stands for bimolecular, so this is the rate determining step, and it's concerted. The standard mechanism for E1, which is unimolecular, is that the slow step is leaving group leaves first. And again, you're going to need a good leaving group for that to happen. That's the slow process. You get a carbenium ion intermediate, and then in a second step, let's just point out, yes, this is a carbenium ion. You want to beware rearrangements. They are often observed in E1 type mechanisms. You don't need a strong base at all. Often it's just the solvent that acts as a base to remove the proton to give you your elimination product, and then the protonated form of solvent. Both of these are examples of what are called 1,2 or beta eliminations, which was a pattern we've talked about last time. Leaving group on the alpha carbon, proton on the beta carbon. Okay. Now, there are such things as 1,4 eliminations. So the idea here is, what if we put a double bond in between, what if we take our starting material and we break apart the beta carbon and the alpha carbon, we put 2 other carbons in between them with the olefin between the 2. So instead of that starting material, what about this one? So here is the leaving group and the alpha carbon. There's the double bond we're inserting. And so here is what used to be the beta carbon, here is the alpha carbon. All right. And this is actually an example of the principle of vinylogy. You ever heard of that? No? I'm not making it up. Vinylogy is that if you take a molecule such as this alkyl halide and you insert 2 carbons with a double bond in between the 2, the chemistry of the resulting molecule is going to resemble this. Okay? So this molecule is also subject to elimination, because a base could remove not the beta proton anymore, but the delta proton in this fashion. Electrons kick down here, these shift here, and then the leaving group leaves. Okay, we have an extra set of arrows, but that double bond is positioned so that, you know, our delta proton is sort of beta to the double bond. So if we remove this, kick the electrons down here, move these here, then the leaving group leaves. And that will give us, an elimination product and the leaving group left. Okay. So we see these kinds of things all the time. An example of a 1,4 elimination would be one of the steps from acid catalyzed aldol. So an aldol product is a beta hydroxy carbonyl compound. If you do the aldol under acidic conditions, instead of the beta hydroxy carbonyl compound, I'm going to draw the enol tautomer. This would be, I suppose, I'll show you the starting materials. This is just acid aldehyde, acid catalyzed aldol reaction. Okay, so here's carbonyl carbon, alpha carbon, beta carbon. Here we've got the enol tautomer. If I protonate the oxygen on the beta hydroxy group, that then becomes a good leaving group. And then, so if this is my leaving group, that makes this the, there we go, the alpha carbon, beta, gamma, delta. I have lone pairs on that delta atom, or if you want 1, 2, 3, and 4. So now those electrons can kick down, these can kick over, and the leaving group can leave. Do you see how that is a similar arrow pattern to what we just did above? All right, so then the leaving group leaves. To give us our alpha beta unsaturated carbonyl compound, which if we remove that proton, there's our product. So that's reasonable arrow pushing, and you may have seen things like that before, but we're sort of drawing similarities to these patterns of elimination. And the idea is, for 1, 2, and 1, 4 eliminations, you need a proton that can be removed such that arrows can push and kick the leaving group off after it's removed. Or you need a lone pair on that beta carbon, or in the case of the 1, 4 eliminations, the delta carbon. All right, questions so far? Okay, here's some other examples of eliminations that come up. Some of these are interesting. I didn't actually know about too much before. This is called, I don't actually know how to say this, whether it's Grob or whether that's like a German B, so it's S or something like that, but this is with 1, 2 alkyl halides. If you use zinc zinc will do an oxidative addition into one of the carbon-bromine bonds and give you this intermediate, and then you can, this can undergo this kind of process. And the reason this is related to an elimination is just you have a leaving group on the alpha carbon, and on the beta carbon you don't have a proton that's being removed, but instead you have something that's not quite a lone pair, but sort of, right? It's in a bond between the carbon and the zinc, and we can use it to sort of kick down and kick off that leaving group, and the product it gives us is the double bond. And this can be done in both sort of 1,2 and 1,4 situations. So this is kind of cute. A 1,4 substituted dibromocyclohexane. 1, 2, 3, 4. Again, if we do oxidative addition with the zinc, let's go ahead and just put the zinc here. I'm not necessarily intending to communicate anything about regioselectivity. Both of those bromo groups are identical because chair flipping changes one to axial and the other equatorial, so we don't really need to worry about which one reacts. In any case, this can fragment as follows. So that in terms of carbon-carbon bonds, the ring opens and you're left with that. Okay, I don't have examples of how that's synthetically useful, but let's see. Some other times where you've seen eliminations would be the retro-aldol. So the aldol is a reversible reaction. The retro-aldol is really actually important in glycolysis if you've studied any biochemistry. So here it's a little tough to sort of figure out the pattern of what we're looking at here relative to what we've seen before. It's almost like this is the leaving group. It's going to leave as the enolate, which would make this the alpha position as we've learned to think about eliminations, and this the beta position. And the point is you've got either a proton that can be removed or a nucleophilic pair of electrons at the beta position that can kick down, make a new pi bond with the alpha position, and then break, and then the leaving group leaves. Okay, does that make sense? Standard elimination. Another one that's really like this, we would call a retro-Michael. So a Michael reaction is a reaction of an enolate with an alpha-beta unsaturated carbonyl compound. The product of a Michael reaction is a 1,5 dicarbonyl compound. 1, 2, 3, 4, 5. If we make the enolate for one of those carbonyls, we can do the following elimination. Breaking the molecule up into the alpha beta unsaturated carbonyl compound and an enolate. This probably looks like a 1,4 style elimination if we say, okay, the enolate here is the leaving group. So the carbon that has the leaving group for a 1,4 elimination we'll say is carbon 1, 2, 3, 4. And then, yeah, at position 4, you've got that nucleophilic pair of electrons that can kick things off. Okay. Question so far? Pretty standard, kind of boring. All right, let's do kinetics. A lot of the kinetic issues for the elimination reactions were worked out in the 1940s and the 1950s. So for standard kinetics for the E2 reaction is that product appearance is bimolecular, unimolecular in alkyl halide starting material, and unimolecular in base. And in general, there is a large primary kinetic isotope effect, deuterium kinetic isotope effect, at the site of deprotonation, suggesting that there is substantial breakage of the of the bond between the beta proton and the beta carbon in the transition state of the rate determining step. All right, so deprotonation happens at the same time as leaving group leaves. In contrast, for the E1 reaction, the appearance of product is generally unimolecular in reactant only. Often you don't need to add base. Often the departed leaving group itself or solvent acts as base. There is minimal or perhaps no deuterium kinetic isotope effect because deprotonation happens after the rate determining step. Okay, and as I said, departed leaving group or solvent often acts as base. So all of that should be relatively familiar. On the subject of the E2 reaction, it's useful to think about, it's useful just to mention, I mean, in this chapter we're not doing substitution, but it's useful to think about competition with SN2 because most nucleophiles are good bases and vice versa. And so you expect there to be sort of both going on. So here's some actual data, which is going to follow trends that you learned in your introductory OChem class, but I thought it was kind of fun to actually see the data, where fun here means that I geeked out about it a little bit because I'm a professor of this stuff. So we're going to look at alkyl halide identity, the identity of the nucleophile versus base, look at the solvent, and then we'll look at the percent of the E2 elimination product versus substitution. I'm not going to write out the substitution percent, but whatever the number for E2 percentage is, the other remaining percent up to 100 is the substitution product. All right, so if your alkyl halide is tertiary, your base is sodium ethoxide, your solvent is ethanol. That's a strong base and a good nucleophile, but you see 100% elimination. Why? Because the tertiary alkyl halides shut down as far as substitution is concerned. If you use, instead of sodium ethoxide as your base, if you use tetrabutyl, yikes, 1, 2, 3, no, that's not a butyl group. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Yeah, I'm not doing that again, I'll just write tetrabutyl ammonium chloride as your base. Look at that, what's the base? Well, it's Cl minus. Cl minus is your base and or nucleophile, not a particularly strong base. Solvent here is just details because these were actual experiments. I'm not sure it changes anything in particular. Almost 100% elimination. Could you rationalize why it's less than 100%? Perhaps because chloro is not as good of a base as ethoxide. The remaining percent, is that actually from an SN2 reaction, or is it perhaps SN1? Maybe, I don't know that they looked into that. And in any case, with this starting material, how would you tell? There's no stereochemistry to distinguish an SN2 for an SN1 product. Yeah?
What allows, I mean, obviously, probably with the tetrabutyl ammonium, what allows chloride to act as a base? Because I think of chloride in terms of the conjugate base of hydrochloric acid.
Yeah. Not a great base. You're in acetone, so that's going to change the pKa a little bit. Also, because you're in, I mean, the acetone is a solvent that can solvate cations, but not anions. There's not really any hydrogen bonding groups. So probably this is an ion pair rather than just the floating around ion by itself. That's going to change things a little bit. Yeah. Okay, so we'll do sort of exactly what you would expect. Let's shift to the secondary alkyl halide. If with sodium ethoxide and ethanol, it's 75% elimination. I remember teaching in introductory OChem 351 that SN2 and E2 are competitive for secondary alkyl halides, but I didn't realize that how much it actually favors E2. And I guess this just reflects the fact that when you have two alkyl groups, that slows substitution just because of sterics. However, for our tetrabutyl ammonium chloride, which we've anticipated is not that great of a base, you got 100% substitution. And this also sort of agrees with what we teach in 351, which is you got to figure out whether your nucleophile is both a good base and a good nucleophile, or just a good nucleophile. Chloro's in the category of it's not really a good base, so it's mostly just a good nucleophile. Okay. And then, excuse me, goodness, sorry. For the primary alkyl halide, again, sort of what you would expect. 9% elimination for sodium ethoxide as a base. In an introductory OChem class, that's usually, we'll just say 100% SN2, but you do see some elimination experimentally. Though, again, if you're using something that's not a particularly good base, you see just substitution. Okay, so that's sort of the SN2 versus E2 story. There's some things we could say about SN1 versus E1. First of all, if you go back and look at the mechanism, the standard mechanism for E1, the first step, which is the rate determining step, is identical to the rate determining step for SN1, right? So what promotes SN1 will also promote E1. But there are some complexities in solvents and with R groups that favor carbenium ions. So by solvents that favor carbenium ions, I'm talking about solvents they call them highly ionizing solvents, solvents that can stabilize carbocations. These are solvents that have nucleophilic atoms in them. Anything that stabilizes the carbocationic intermediate favors both the SN1 and E1 reaction. And the ratio of SN1 to E1 products is typically independent of the leaving group, which means that the bifurcation from, say, an E1 product versus an SN1 product happens via this common intermediate. So if that's true, the leaving group shouldn't matter at all. Other factors determine the ratio of E1 and SN1 products. So you could take the same starting material, swap out the leaving group, and it isn't going to change the ratio of your SN1 to E1 products. That story is a little bit different if you're in a solvent that does not stabilize carbenium ions, because in that case, instead of this carbenium ion intermediate, what you likely have is an ion pair. And in that case, the ratio of SN1 to E1 products actually does depend on the leaving group, because the leaving group's still involved in that carbenium intermediate. It's not just a naked carbenium ion, it's the ion pair, and so the leaving group does play a role. That's a little subtle, it's kind of deep into the literature, but it is an example of how ion pairs can make things more complicated. All right. All right, next we need to talk about the E1CB mechanism, and we're going to get back into a little bit of kinetics and steady state approximations, which I know you've missed. So E1CB stands for unimolecular elimination conjugate base. And calling this unimolecular is a bit of an oversimplification. When does this happen? Generally, remember, if we're talking about the leaving group is on the alpha carbon, generally for E1CB reactions, there will be an electron withdrawing group on the beta carbon, adjacent to the beta proton. And so an example of that is where this electron withdrawing acyl group is attached to the beta carbon that's adjacent to the alpha carbon that has the leaving group. When this situation happens, the beta proton is more acidic than expected. Because of that, the elimination reaction works with weaker bases than are typical for E2 reactions. And another observation for E1CB reactions is that the reaction works even if your leaving group is poorer than expected for, say, an E2 reaction. And the mechanism of the E1CB reaction here, in this particular example, we're using triethylamine as a base, which is a weaker base than you would typically use for an E2 elimination reaction. You first remove the proton that's beta to the leaving group. In this case, it's alpha to a carbonyl, so you're essentially making an enolate. Once you've made that enolate, you're now in a situation where you can kick the leaving group off. Oops, there we go. And again, sort of keeping track of our atoms and where we've been. This is the carbon that has the leaving group on it. This is the beta carbon that we initially removed the proton from. All right, so that's a classic E1CB reaction. Now let's talk about kinetics. And to facilitate this, let's just draw out a general scheme. So leaving group on the alpha carbon, electron withdrawing group on the beta carbon. We have a base. It's going to remove a proton. There's a forward rate and a reverse rate. The electron withdrawing group stabilizes the carbanion, and then there's some K2 elimination step whereby we form the double bond and the leaving group leaves, and there's our product. Okay, does that sort of make sense? Now, if you do the steady state approximation on this negatively charged carbanion intermediate, and then do what we did in the earlier chapters, you can come up with, we won't do the algebra, I'll just show you the result, with the following expression for the rate of the reaction. In the denominator, we have K minus 1 times the concentration of conjugate acid of our base plus K2. So that's more complicated than advertised, because in the name E1CB, so you're told it's unimolecular, but that rate law doesn't look unimolecular. So let's talk about the various complexities here. All right, so situation 1 is, let's suppose that the backwards rate, K minus 1, is much, much greater than K2. If that's true, then this rate law simplifies. We get rid of the K2 term, it simplifies to this. And it turns out that we find the ratio of base over conjugate acid to be in the rate expression. And if we know the Ka for the conjugate acid of our base, we can sort of simplify or substitute in to this expression the following ratio, Ka over the concentration of H3O plus, which tells you that again, if the rate of the reverse reaction, that is reprotonation, is much faster than the forward reaction to do the elimination, that is, if this deprotonation step is reversible, then we see that the rate of the reaction doesn't actually depend on how much base concentration we have. Instead, it depends on the pH, or if we keep the pH constant, the reaction doesn't depend on how much base we have. Now, you've seen kinetics like that before. That is a hallmark of specific acid or base catalysis. Remember, that's where the proton transfer happens prior to the rate determining step. So if the K1 reverse rate is faster than the K2 rate, that means proton transfer is reversible. then we see all of the hallmarks of specific base catalysis. So the kinetics are unimolecular in our starting material, but depend on pH and or the ratio of base to conjugate acid. And this is a specific class of an E1CB reaction. They call it E1CB with an R for reversible. And an example of a reaction that follows this kinetic scheme is the E1CB elimination of methoxide from this molecule to give you this alpha beta unsaturated carbonyl compound. Okay, so we have just a little bit more to do on E1CB. There are 2 more class periods after this one, and then we will be done. So you are almost there. Congratulations.